Greetings. We have built up some information in our previous video, and now we shall continue with the rest of the combustion problem here. Now, the next step is to calculate entropies for both reactants and products. And fortunately, the third law of thermodynamics gives us a common basis for entropies of different substances, and that is 0 Kelvin. So, and that is the basis we have been using throughout up until now for reading different entropies from the tables. So, what we have to do is just to read different entropies for different reactants and products here. And if we do that from the tables, these are the values that we get. The only difference is that what we have is not pure substance the um, at the um, atmospheric pressure, as all the values are given. These are substances at different pressures because we are assuming them at their partial pressures. The way to account for that change in pressure from the standard pressure is simple. We just have to calculate minus RU ln yi times P mixture divided by P0, which is the standard pressure. Now, what we have done is to assume that the mixture pressure is 1 atmosphere. It means that for fuel is at 1 atmosphere, air is at 1 atmosphere, and partial pressures are accounted for in O2 and N2 as compared to 1 atmosphere, and we also assume that product is at 1 atmosphere here. So PM equals P0. These two cancel out, and all we need to calculate is RU ln yi for each of the constituents. That would be pretty simple, and that's what I have done here in this table for each of them. We have y here, yi we have already done here, and just we take a logarithm and then multiplied by RU, which is 8.3144 kilojoules per kilomole Kelvin, and this is what we get. Now, you see, these values are the entropies of each kilomole of the constituent that is shown. So this is the entropy of each kilomole of C2H4. This is the entropy of each kilomole of oxygen. This is the entropy of each kilomole of nitrogen, and so on. Now, add these two together, and you would find the entropies of each kilomole of each constituent. You see, these are the entropies. I mean, 193 is the entropy of N2 in the mixture. Okay, 324 is the entropy of CO2 in the mixture. It is entropy of each kilomole of CO2 in the mixture. Now, multiply them by their number of moles, and here we would have the entropy, the total entropy of that constituent in the mixture. Okay, so the entropy of C2H4 in the reactants is 219. The total entropy of O2 in the reactants is 784.83, and so on. But all these are the entropies of different constituents for every kilomole of C2H4. Although I haven't written here kilomole, but all these calculations, I mean, even this kilojoules is for every kilomole of fuel. Every kilomole. I mean, we are using kilomoles twice in two different terms. First is here when we say that it is 3.6 kilomoles of O2 in the mixture, and therefore each kilomole of O2 has an entropy 218, and therefore the total entropy of O2 is 78483. But this 78483 kilojoules per K for um, O2 is calculated for every single kilomole of C2H4. So writing it here, we could do it as sigma S for reactants equals 1 kilomole of fuel times 219.83 plus which the value of it would be here. I mean, the value of each term that I'm writing now is calculated in this row plus 3.60 kilomoles of O2 times the entropy of each kilomole of O2, which is 218.01 plus 13.54 times 193.46, and that's the entropy of the nitrogen, and that's what that equals 3623.36 kilojoules per K. But for every kilomole of fuel. I mean, this is also for all different kilomoles of all the uh, reactants. But you see, this is calculated for every single kilomole of fuel. We have this value written here. And also, we could do the same for the products and calculate it, and the outcome would be 4072.95. Sigma S for products is 2 times 334.71 plus 2 times 289.03 plus 0.60 times 301.50 plus 13.56 times 258.66, and the outcome would be 4072.95 kilojoules per kilomole of fuel times Kelvin. You see, this kilomole is the per kilomole of fuel, which is different from the kilomoles that you're calculating, you are accounting here. All these values of kilomoles are per 1 kilomole of fuel as we have written it here. Now, the final practice that we could do in this term is to write down the second law of thermodynamics, and that is zero, which, as we assume the combustion to be steady, equals all the entropies of the those that enter the control volume, minus all the entropies of those that leave plus Q over TB and plus S gen. Now, there are delicate points in the writing of this equation. Of course, we have achieved a great deal by calculating SI and SE, which is just SR and SP that we have done here. This would be 0 equals 36 to 3.36, which is the entropy of the reactants that they enter the control volume minus 4072.95, which is the total entropy of those that leave our control volume, plus now, this is interesting because we have a heat transfer, we have calculated our heat transfer before, and we know that our heat transfer is minus 14,544 kilojoules per kilomole of fuel. But what is the temperature of the boundary of this combustion? You see, if we take in some books, it's written that this temperature is 298. And what they have done is that they have calculated it for a boundary away from the combustion chamber, that is 298. And by accounting this boundary, by taking this boundary, they have accounted for two entropy generation mechanisms. First, combustion. Second, heat transfer to the surrounding, because the heat transfer to the surroundings is also included in this boundary. Now, if we assume some sort of temperature here, then what we would get is that we would exclude some of the entropy generated for this heat transfer, and we would all account for uh, the uh, entropy generation for the combustion. And combustion products are at 2 to 50. And what we could do, we could just account that value because the heat transfer is between some combustion products at 2 to 50 and the surrounding at 2 to 298. If we exclude that from our calculation and we account this boundary to be at uh, 2 to 50, as we have assumed that combustion products, that the generated entropy that we calculate would be our generated entropy of the combustion. Now, calculate the value for Sgen from this equation, and Sgen would be 456.054 kilojoules per kilomole of fuel, C2H4, times Kelvin. You see, uh, there's a comment to make on this value. Usually in our previous problems, when there was heat transfer involved or there was friction involved, the values calculated for entropy generation was in the order of 1 or even often less than that. Now, a value of entropy generation for every kilomole of fuel of 456.04 is very high. And that's important to note that such a high value is typical for combustion problems. In fact, if combustion is involved in any problem, then the value of the entropy generation and the irreversibility of uh, combustion would basically overtake all other irreversibilities that might be present in that problem. And that's a very important point to take care of. Combustion is perhaps the most irreversible process that we can find. Anyway, thanks very much for watching and cheers.